Okay, you can record now if you want. Yeah, go ahead, Jack. No worry. Thank you. Okay. All right. Anyone else? Aaron.
May I record as well, Professor?
Yeah, go ahead, Wilson. I give you that permission already.
Oh, I'm sorry. I stepped out.
All right.
All right. Thank you.
Yep, go ahead, Aisha. I already gave you that options. Go ahead, Derek. I already did that. Okay, so let's get started. Okay, so probabilities, right? In 5.2, we talk about union probabilities where you're adding, right? So the keyword is, if you seeing the question asks you find the probability of A or B, meaning that you need to add the two probability, and just to make sure checking that they have nothing to share in common, so that you don't have to subtract what they share. If they share something, then you need to take those away before you add the two probabilities, okay? The formula is provided. And then in 5.3, we talk about independence and multiplication of probabilities. So if they are independent, then they will be multiply the two probability together. And the keyword is A and B, right? So we said find the probability of A and probability of B, then you're gonna multiply the two together, okay? So now we look at 5.4, which is conditional probabilities, and also the general multiplication rule for probabilities, right? All right, so conditional probabilities mean that instead of look at the whole population, we look at the shrink population, right? So we know what's going to happen already, and then we just focus in that area. So for example, instead of looking for whole California, we just said, okay, now focus on Fullerton College only, okay? So that's the condition, right? So I don't want the student to go around, throughout California to search for the answer. I said just focus on Fullerton, and that is what we call condition, right? So that condition will be given. So the keywords in here will be look out for what is given. All right. So now let's start building up this section 5.4 slowly, right? So suppose I have, when you're rolling a dice, and then I want to get a number 6, okay? What will be the probabilities of getting a number 6 when we roll a dice?
1 out of 6.
1 out of 6, right? Okay, so that will be 1 out of 6. So the probability of getting a 6 equal to 1 out of 6. All right, so that's normal. We learned that before, right? Now, if I'm telling you that, okay, I roll a dice and I can see it, and I give you the hint, and I said, well, the outcome is an even numbers. Now, what is your chance of getting number 6 after I told you that hint right there?
1/2. 1/3.
1/3. Okay. Okay. So if the outcome is an even number, then the new outcome will be 2, 4, and 6. So the probability of getting a 6 have been increased higher, which is 1 out of 3 chance. And this is what we call conditional probabilities. Make sense? Right? So we focus on the new information from that original problem. Okay. All right. So that's just one example to start off with, right? So kind of give us a better understanding what it means by conditional probability. So you can see here, I don't focus on all the outcome 1 to 6 anymore. I just focus on the even outcome, which is 2, 4, 6. So now we can totally get rid of 1, 3, and 5 because 1, 3, and 5 not going to be useful here, right? Because we know the outcome will be an even number already. So that's what it is. So put everything together, right? So we have the formula for conditional probabilities, all right? So you might see the notations, P, parenthesis, F, and then the vertical bar, and then E, okay? So that vertical bar stands for given, okay? So that's vertical bar stands for givens. So we will read it as find the probability of event F given the event E already occurred. Okay, so we already know the outcome of the event E. So now we just need to find the probability of the event F. Okay? So in the formula we're going to use will be P of F given E will equal to P of F and E divided by P of E. So we have to find what they share in common divided out the new outcome, right? So you can see here the new outcome as I show you up there will be 3, right? So that's what it is, right? So divided by the new outcome, all right? So you have to find out what they share in common, right? What they share. And then divide by the new outcome. That's all we're going to be like that. So the given condition will always be in the denominator, okay? And then the one, what we ask will be the one in front, right? So F given E will be P of F and E divided by P of E. Are we good for that formula? Yeah. Okay, so let's take a look at the next example. All right, suppose we have F and E are 2 events, and P of E and F upon 3, and P of E is upon A. So what is P of F given E? All right, so we start off with the formula. Right? P F given E will equal to P of F and E divided by P of E. So now we're looking at what they give us. They give us P of E and F, so that's good to go. So you have 0.3, and P of E alone is just 0.8, and then we divide those together, and there we go. So now we have 0.375. And we know it's still good because the outcome, the final answer is still less than 1 and more than 0. So we know we're on the right track. Okay, so that's how we use the formulas. So I'm gonna use that formula and then go back to example 1 to see if we get the same answer, all right? So remember what is given, right? Right. So now we want to find out the probability of getting 6, given that it's an even number. Okay, so that's what we want. All right, so now you can see here, this equal to the probability of 6 and an even number divided by the probability of even number. So if you look at the faces of the dice, you got 1, 2, 3, 4, 5, 6. So even number, there's only 3 of those, so we get 3 out of 6. And then 6 and even, there's only one choice, right? So we get 1 out of 6. So when you have 1 out of 6, divide by 3 out of 6, so we multiply 6 out of 3, and we're getting 1 out of 3, same. So when we start the problem, we found the probability based on logic, right? But then we can also get the same answer if we follow the formulas, right? So the formula said find the probability of getting a 6, given that it's an even number. So we have to find out what's common between getting a 6 and an even number. The answer is it has to be number 6, because number 6 is 6 itself and also an even number. So we have 1 out of 6 chance for that. And then in the denominator, we look at the probability of an even number. So even number in a row of dice, you got 2, 4, and 6. So now you got 3 out of 6 chance of getting an even number. So there we go. When you put those together, 1 6 over 3 6 is equal to 1 6 times 6 3, and we get 1/3. So that's purely based on the formula. Then when we look at the logic, right? So we know the outcome is an even number, then you only shrink it down to 2, 4, 6. And now I got 1 out of 3 chance to get that even numbers. Make sense? So that's how we use logic together with a formula of conditional probabilities to explain all of this, all right? Any questions before we move to the next example?
I have a question.
Yes, go on.
Why do we multiply the 6/3 to the 1/6?
Yeah, because that's the rule for dividing a fraction. When you divide a fraction, you multiply the reciprocal. That's the rule. Yeah.
Okay, thank you.
Yeah.
So according to the formula, we have the probability of getting a F and E divided by the probability of getting E, right?
That's right. That's right.
Now, when we actually applied that to the situation of getting a 6, given that we have an even number, all we did was divide the probability of getting a 6, which is 1/6, divided by the probability of getting even, which is 3/6.
That's right.
We didn't do any multiplication in the numerator.
Oh no, because we are dividing, right? So the key is right here.
In other words, I'm having a hard time understanding the numerator as getting a probability of E and F. It looked like it was just the probability of E.
Oh, so that will be a different situation here, Grayson, because the other one where we are selecting 2 cards. What is the chance is gonna be a 6 and an 8? So that would be 2 consecutive cards. Still
Okay.
only look at one option. We only select one option, which is there's only one thing that they share together here.
Got it.
Yes. Okay. All right. So example 3. Here it is. All right. So we're gonna do it based on the formulas and then we're gonna do it based on the logic that we're gonna use the table for. Okay. All right. So if we do based on the formula, so if you notice here, we always divide it by the total. Okay. If you do based on the formula, we always divide by the total. If you do it based on logic, then we have to shrink down our conditions. All right. So I'm gonna show you both. Now, the table below is presenting the marital status of male and female 15 years old or older in the US in 2010. All right. So we have here is contingency table, right? The column present the male, the female, and here's the total, and the row presenting a different category: never married, married, widow, and divorced and separated, right? And so on. Okay, so let's see, we can play around with this, right? So based on the table, find the following probabilities. Now, what is the probabilities of divorce, right? So when you want to find the probability of divorce, you're gonna look at the divorce column, right? So we know that there will be a 23.8 out of 242.2. So I wanna build this, I'm saying, well, probability of divorce will be 23.8 out of 242.2. So, I'm just gonna leave it there into a fraction so we know what to do later, okay? Now, I want to find out the probabilities of divorce given that the individual is a male, okay? So you can see here, that's the condition, right? Given that, so that's the condition. Right? So you want to find P of divorce given that it's a male. So by the formulas, right? Probability that divorce given that it's a male equal to probability of divorce and male over probability of male, right? So that's the formula. Right? So we have to find out what they share together divided by the given conditions. All right, so now we have to look at the table, divorce and male, and see where do they intersect each other. So this is divorce, right? And then I'm looking at male, right? So we look at divorce and male. So here are the divorce row. And here are the male, right? So when we look at those two column and row, we know that they do intersect each other, and the place of intersection is 10, right? So that's what they share. So that's what they share together. All right, so I have here 10 over 242.2 divided by male will be 117.8 out of 242.2. So we go with the formula. So that's what we're gonna get, right? So you look at what they share with each other. So they share 10 millions, and then divide by the given condition, which is 117.8 out of 242.2. And same concept, when we are dividing, we multiply the reciprocal of the denominator. So I have 242.2 divided by 117.8. And there we go, 10 over 117.8.
I have a question. So
Yes.
couldn't we just go straight to doing 10 divided by 117.8? Because
That's what I
that's
just
where the
mentioned
divorce
before.
doesn't nail.
Well, that's what I just mentioned before. We're gonna do with the formula first, and then we use the logic to later.
Oh, okay, gotcha.
Okay, makes sense for the formula, yeah. Adam, it's just gonna be one condition here, right? We look at something very simple.
Are
All
these
right, so-
answers, sorry, are these answers always going to be in fractions, like on the homework and stuff?
I think they prefer a fraction. If they ask you to put it in decimal form, you go ahead and put it in decimal form. Yes.
Okay.
Yeah, but for me, just leave it on fraction on the exam. I'm cool with that. All right. So if you look at what is called the table that we went through, right? Let me bring that back real quick. So you can see here in sections 4.4, when you talk about conditional distributions, right? So look at this, what we did, right? So construct the conditional distributions table graded by the method of delivery, right? So when we look at the method of delivery, we look at traditional model, online model, and hybrid model. And I want to find out how many students got an A's in the traditional model. What we did was we take 36 and divide by 237. So we did conditional probability before chapter 5, which is section 4.4, but we didn't have that, a direct definition of what is conditional probability is about, right? But we look at conditional distributions table, and that's what we did. So now if I go back to chapter 5 and say, well, if I want to organize, conditional distributions, then I would take 40.2 divided by 117.8, and then 62.2 divided by 117.8, and then 10 divided by 117.8. And then I ask you, what is the probability of divorce in that column? You would tell me it's 10 over 117.8 million, right? So that's what we did, right, in section 4.4. So and that's exactly what conditional probability is about, right? So now we get 10 out of 117.8. So we first started with the formula to show you exactly what it means by look at conditional probabilities. And then when you use the logic, you said, okay, I know the focus is on male, so I will have 117.8. Now I want to find out that in that 117.8, how many are there that divorce? I can just get 10 divided by 117.8, right? So that's how you use the logic in this conditional probability scale. Does that make sense, guys? Right, with the formula and then with the logic itself, there we go. All right, so for part C, all right, and D, please go ahead and do it using the formula. The logic is easy to see, we can see it right away. Please go ahead and use the formula so that you can practice that out, right? Because sometimes on the homework, they're not gonna give you the table, they're gonna give you a situation, and then you're gonna use the formula to do it, right? So practice yourself with the table instead of the logic, but then use the logic to check your answer, all right? All right, take about 5 minutes here, and I'm gonna show you the answer in 5 minutes.
Are we doing C and D?
Yes, please. All right, please check the answer. You got the same? Thumbs up real quick. Thank you, Grace.
I'm confused by the second one. D.
Uh-huh. Yeah, so for D, the condition is never marriage, right? So because female and never marriage, they share the same anyway, right? So 34. And then never marriage, so you have to look at the whole set of never marriage, right? So the never marriage, you have 74.2. So you have to look at the sum of never marriage. So when you look at the sum of never marriage, it's actually 74.2 million out of 242.2. So we look at the sum of the row instead of sum of the column. Does that make
Yep.
sense, Matthew?
Yes, sir.
Mm-hmm. And that's the reason why, you know, when we did the chapter 4, right? So at first I gave you by the method of delivery, and then second I asked you to do extra, like not by the method of delivery anymore, but by the grade distribution. So now we don't divide by the column, but we divide by the row. Yes, and that's the connection with 5.4. So when you look at that options, that's what we got. Okay, better now, Julia.
Yes.
Uh-huh. So, you know, the reason I do in C and D, just to show you that, you know, even though they focus on the same topic, never marriage and female, however, you know, when they flip around the condition, the probability also change. And that's explained in chapter 4, right? When I look at the sum of the column versus I look at the sum of the row, right? So you look at this one here, you look at the column Y, you take 36 divided by 237. But you look at the row Y, you take 36 divided by 99, depending on what is the condition we focus on, okay? All right, so that's what we call conditional probabilities.
I have a question.
Yes.
For C, on the denominator, why did you select 74.2 for females?
For D or E or C?
C.
Yeah, female, you have to look at the female column, right? So you have to look at how many female are there. So in the whole female, you have 124.4.
Oh, got it. I wrote down the wrong one. Sounds good.
Mhm.
Professor, do you mind scrolling up to example 2, please?
For sure, Walter.
Alrighty, thank you.
Mhm. Okay, is there any other questions? Okay, so here is the formula for a general multiplication rule when the two events are not independent. All right, so the probability that two events E and F are not independent and they are both occurring will be P of E and F equal to P of E times with P of F given E. So Grayson here to answer your questions, right? So why for in 5.3 we multiply the two probabilities, but here we don't? Well, the reason is they were independent in 5.3, but in 5.4 they are not independent. So therefore we cannot treat them as they are independent from each other. Does that answer your question now, Grayson?
I think so, yes.
So now if they are not independent, we have to take P of E times with P of F given E, and that will give you P of E and F, all right? So in general, that's what we do. So in summary, the rule of probabilities one more time, right? So we have any probability will be bounced between 0 and 1 inclusive, and P of E or F will be P of E plus P of F if they are disjoint, right? So remind ourselves again, disjoint means that they share nothing. And if they share something, then you need to take away what they share with each other. And then the rule of complements will always be 1 minus P of E. And then P of E and F will be P of E times P and F if they are independent. And if they are not independent, then you have to take P of E, multiply the conditional probability of F given E. Okay, so every situation will have a formula to follow. So if you want, as I mentioned before, right, the keyword is very important, right? So the keyword is very important. So when you see R, you always add. When you see N, you always multiply, right? That's the keyword. When you read through problems involve probabilities, because using the understanding the wrong keywords can cause a lot, because when you take 2 plus 2 is 4, right? I mean, wrong example, right? When you take 1/2 plus 1/2, you get 1, but then when you take 1/2 plus times 1/2, you get 1/4, right? Matthew was laughing when I shout out 2 and 2 because they are special case, right? Yeah, okay. So just watch out for those little details. All right. So that should be the end of 5.4. All right, any question on that so far? Sounds good. All right. So, 4.4 is pretty much 5.4 modification on that, right? Now, 5.5 and 5.6, we're looking at counting technique, right? And also looking at how to find the probabilities more than one subject was select, right? So what we've been so far, we're just selecting one subject at a time. Now we're gonna move it to say I can select like 5 objects, I can select 6 objects. So how am I going to find the probability of those things? So to remind everyone again, this is a deck of cards, and we're always gonna have 4 different suits, right? Club, spade, heart, and diamonds. And then we have 40 numbers cards, and then we have 12 picture cards. And each of those suits will have 4, right? 4 cards, right? 4 of the A's, 4, 2, 4, 3, and so on. Okay, and we will have 26 black cards and 26 red cards. Right. So when they talk about 26 red cards, you're gonna think of 26. Right. So everything else will have that 13 club, 13 spades, 13 hearts, and 13 diamonds for each kind. Okay. So if you're not familiar with deck of cards, that's all the information that we can pull out from a regular deck of cards. Okay, so now we're gonna count, right? So solve the first part of this section is solve counting problem using the multiplication rule, right? So suppose that you have 1 favorite jeans and then 2 favorite shirts, right? How many different ways can you wear your favorite jeans and shirt? Right, so I'm start with something very simple here so we can see the logic behind it, right? Right, so we only have 1 jeans, right? We have 1 jeans and we have 2 shirts, right? How many way we can wear? Well, the only thing you can do is jean and the first t-shirt or the first shirt, or jean and the second shirt, right? So that's something that you can wear or only, right? So jeans together with the shirt number 1, or jean with the shirt number 2. You only have 2 options. Right, so total we only have 2 options. All right, so now we're just starting build up what is counting is. All right, so example 2, how many ways a boys and girl in a 2-child family can have? Okay, so this one similar to flipping a coin, right? Head or tail, right? So when we look at these possibilities, right? So the first child, right? So we look at the first child. We only have two options. Could be a boy or a girl, right? Okay. And then we look at the second child. So we have a boy or a girl. So this one will be same thing, a boy or a girl. So if you look at the outcome, you get boy, 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 girl, girl and a boy, and then girl and a girl, right? So we have 4 outcomes. Okay, so we have 4 outcomes. How about a 3-child family? Okay, so same thing. How many outcomes are we expecting to have? So you can see here boy and girl, and then boy and girl, and one more option, boy and girl, boy and girl. So here boy and girl and boy and girl. All right. So now if we look at the outcome, let's see how many are there. Right? All right, so we have boy, 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 right? So boy, 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 and then you get boy, boy, and girl, right? Right, boy, 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 and girl, right? And then now we get boy, girl, and boy, and then boy, girl, and girl, right? Okay, so that's done with the left branch, and then go to the right branch, you get girl, girl, and girl. And then we get girl, girl, and a boy, and then we get girl, boy, and a girl, and then girl, boy, and a boy. So now you count the total outcome, so we have 8 outcomes. So that's not bad to list out the tree diagram and count how many outcomes do we have. But then you can see here, we increase it more and more. You're gonna run out a lot of space if you keep doing the tree diagram like that. All right. So again, we still slowly build up the general definition here, right? All right. So here, example 3, we want to look at how many ways of meals can be ordered as a fixed price restaurant if there will be 3 choice of the appetizer, 5 choices of entries, and 4 choice of dessert. All right, so now if you want to list out the total outcome, it's gonna be a pretty long time, right? Okay, so we try to see. All right, suppose like I want to have 3 choices of appetizer. So we have A1, A2, and then A3. And I have 5 choices of entry. So I have E1, E2, E3, E4, and then E5. And I have 4 choices of dessert. I will have D1, D2, D3, D4, right? So if you, for example, you walk into a restaurant and you pick a plate and then you're gonna go and pick your choice, you pay just one price. All right, so let's have a feel and see how crazy this could be, right? So I'm gonna have A1, right? I pick my appetizer and then I can pick the first entry. So I get E1 and I can get the first dessert. So I get D1. However, I can change my choose a little bit. I can have A1 and then I can have E2 and I can have D1, right? I can have that. Or I can have A1, E2, and then D3. I can have A1, E2, and then D4. So I can do something like that, right? I can set, well, I change it a little bit. I can have A1, E1, and then D2. I can have A1, E1, and then D3. I have A1, E1, and then D4. Right? So that's also another option I can choose, right? And so on, right? So you can see here, that's gonna be something crazy to count all the combinations. So therefore, it would be much better if we can develop some technique that will make us get the number easier. And that technique is what we call fundamental counting principle. Okay, so the fundamental counting principle stated that suppose we have first selection, we can do it in P different way, and the second selection we can have Q different way, and so on. So the total number of way that we can form the outcome will be P times Q times R. And that's what we call total fundamental of counting principle. So now if we go back to example 3 and said that, okay, I have 3 choice of advertiser, 5 choices of entry, and 4 choice of deserve. So if I want to find out everything, I will have the total outcome will be 3 times 5 times 4. This will give me 60 different outcomes. Yes, Matthew.
How would that apply to example 2?
Yeah, I'm gonna go back to that in a bit, Matthew.
Oh, my bad.
So, Adam said, well, let's choose 60, right? And that's right? Because of we have that option. So if we have that many number away for the first one, second one, and third one, that's all we do, right? We multiply them together. So, multiply 3 times 5 times 6 to get 60 would be much better than we list out all the possibility as I show you right here in example 3, right? So that would be a better option for us. So now to answer Matthew's question, so how do we do that in example 2, right? So in example 2, you can see here, when you have the first child, right? So you have the first child right here. How many options do you have for the first child, Matthew?
2.
That's right. How about the second child?
2 again.
Okay, what's 2 times 2? Oh. All right, how about 3-child family? So you can see 2 for the first child, 2 for the second, and then 2 for the third. So we have 8. So
Got it. I was looking at it wrong.
you're adding?
I was doing 2 by 3, so 6.
I see. Yeah, so we're gonna multiply them. We're not adding, so that's not 2 times 3. Okay, everyone's good now? All right, so let's go ahead and see if we can do in the some multiplication rule here, right? How many different student ID number can be generated if each ID have a number where the first digit cannot be 0? Okay. So how many student ID can be generated if each ID have 8 number and the first digit cannot be 0? All right, so we have 1, 2, 3, 4, 5, 6, 7, and 8, right? So each ID has 8 numbers, and the first number cannot be 0. So when you talk about the digit, right? So when you talk about number system, when you talk about number, we're gonna go from 0, 1, 2, 3, all the way into 9, okay? All right, any thoughts on this?
90 million.
90 million. All right. All right, how you got that answer, Matthew?
9 times a bunch of tens.
9 times a bunch of 10. Okay, very good. All right. So 9 times a bunch of 10s. Is everyone's okay with Matthew answer? All right, you better
I
agree
don't.
because that's the correct answer.
I
So
don't
we got
understand.
9 0 0 0 0 0 0 0. Yes, Walter. Yeah.
I'm not really understanding how that works.
Okay. So the key here is that the first digit cannot be 0, right? If you look at a number system, Walter, if you look at the first digit and you cannot have the 0, how many options do you have left for choosing the first digit?
You have 9 different options.
Exactly. Yes.
Mhm.
Now for the second digit, so since there's no restriction on the second digit, now how many options do you have to choosing a random number between 0 and 9?
Oh, a lot of them.
Right. So now we
Yeah.
got 10 options. Yes. And then the third one, how many options do you have now?
10.
10. And that's keep
Yeah.
going to the last digit.
Mhm.
Is that okay? All right, good. How about the rest of the class? You are okay with that? Sounds good. Okay, for B. All right, a social security number have the format N1, N2, N3, N4, N5, N6, N7, and 9. So technically, it's going in order of 3, 2, and 4. All right. So each of the option can be represented by an integer 0 to 9, assuming that the first digit cannot be 0, right? The first digit cannot be 0, and all digits cannot be repeated the same. For example, this option will be very bad because you wouldn't want to have that social security number generate like that because it's easy for anyone to steal it, right? So how many such number are possible? Okay, so we got 1, 2, 3, and then 2, 2, and then 1, 2, 3, and 4. So same concept. The first digit cannot be 0, so I know for sure it will be a 9 here. All right, how about the second digit? How many options do we have here?
9.
No.
You have 10.
10.
How can it be 10 options if we can't repeat?
Well, how do you know that which one it says not repeat?
I thought it said it can't repeat.
It said
digits
all
can't-
digits cannot be repeated at the same time. So
Oh,
1 1 1 1 1 1 1 1 1 is not allowed, right? That's one of the examples.
got it.
Okay,
In this parameters, can we do 1 1 1 1 1 1 1 1 2?
that's right. That's allowed. Mhm.
Got it.
All right. So how about the third options?
Ten.
Would it still be
10.
10?
All right. So this guy, is there any restrictions? 10. This one also 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 10. Right? But that's also include the 1, the 1, the 1, the 1, and the 1, right? Or the 2, the 2, the 2, the 2, 2, and 2. Or the 3, 3, 3, 3, 3. Or the 9, 9, 9, 9, 9, 9. Yes? So how do we take care of that? Options.
Subtract the ones you can't use, so subtract 9.
That's right. And that will give you an answer. Okay, does that logic make sense? Okay, so here we go. We need to take away 1 1 1 1 1 1 1 1 1 2 2 2 2 2 2 2 2 2 3 3 3 3 3 3 3 3 3 and so on until you get 9 9 9 9 9 9 9 9. So if you take away all of that, there's only 9 outcome. Yes, and that's the reason why we subtract 9 away. Make sense, Grayson? Yeah, because when you said only 9 option for the second one, meaning that you say, oh, we cannot repeat, but then which one do we know that we need to throw away? We don't know that yet, right? So we said just do it normally, but then say now let's throw away the one that repeated itself throughout the series, and that will be 9 outcomes total. And that's how we use that logic to do that.
Yeah, I misunderstood it. I thought that whatever number came next couldn't be a repeat of a number that came before.
Yeah, that would be non-repeated. The next
Yeah.
one.
Okay.
Okay, how about the rest of the class? Are you guys okay? Can I see a thumbs up? Yeah, all right, with the logic so far, very good. Thank you, Matthew, for sharing that. All right, now counting without repetitions. So how many different ways can 3 people be arranged in a row for a group photograph, right? So again, when you make the arrangement for a group photograph, you cannot move, right? So for example, we have a first slot here, we have a second slot, we have a third slot, right? So how many ways can I put 3 people in the first slot? 3 options, very good. So I have a 3 here. How many ways can I put in the second slot? 2, and then I only have 1 option left, right? So the total outcome will be 3 times 2 times 1. So we got 6 outcomes. Make sense, everyone? Yeah, because think of the logic, right? So the first position, any of the 3 friends can be in the first position. But then if the first one of the 3 already chosen, I'm going to be in here, then now you only have 2 friends left to choosing for the second position. So if another one say I'm going to sit in the middle, and then there's only one option left for the last one, right? Right. Remember degree of freedom, right? We talked about that before, right? So when I give you 4 options to choose from, then the first person was selected. Well, that person can pick a $1, a $5, a $10, or $20. So that 4 choice. But then one of the choice taken, then the next person can only have 3 choice left, and so on. So same thing here. And that's what we do with counting. When we're counting on that, okay? There we go. All right, how many different way can 5 books be arranged on a shelf? So we have 5 books to be arranged on the shelf. So what's that gonna be? Anyone? Grayson said 120. How you got that 120, Grayson?
5 times 4 is 20, times 3 is 60, times 2 is 120, and then times 1.
There you go. Make sense? Okay. So you don't believe it? Later on, once the class over, take 5 books and do the arrangement to see how many ways you can actually do 120 ways. Okay. Yeah. So you guys see the difference between counting with repetitions and counting without repetition? Yes. All right. Yeah. So very, very important. Now, the next one is what we have, factorial, right? So factorial, what you're going to see is the exclamation mark right there. In mathematics, it stands for factorial. So factorial defined as a multiplication of itself to the next consecutive number until 1. So I have n factorial will equal to n times n minus 1 times n minus 2 times n minus 3 times 3 times 2 times 1, and that will be the result of n factorial. Very special, 0 factorial will equal to 1, because factorial is the same thing as how many ways we can rearrange something. So how many ways can I rearrange the number 0? Only one way is by itself. Therefore, 0 factorial will be 1, yes? Now, when you think of example B here, when I ask the question, how many ways can I arrange 5 books on the shelf? So we have 5 times 4 times 3 times 2 times 1. So that's just pretty much 5 factorials right there, yes? And that's the concept of that, all right? All right, so 3 factorial will be 3 times 2 times 1. So we got 6, right? How many ways can I arrange 3 people for a photograph? And so time here, 5 will be 5 times 4 times 3 times 2 times 1. There we go, right? So we got 120. 10 factorial, there's no difference. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. There we go. All right. Okay, so if you have a small number, it's easy to do it by hand, but you have a large number, it's harder to do by hand for that multiplication. You can use calculator for that, right? So for example, I want to do 10 factorial. I just press 10, and then I hit math, and then I go to probabilities, and when I go to number 4, that stands for factorial. And that's something I can just press enter, and there we go. All right, so that's how you use a calculator to do the factorial, right? So you check the math again, 5 factorial. 120, just like that. Sounds good? Yeah? Okay.
Is there a formula to figuring out the factorial besides the calculator?
Yeah, so we're
Like
gonna,
besides long way writing?
no, that's the way. Yeah, that's, you want to do by hand, you're gonna do 10 times 9 times 8 times 7, yes. So that's why when you have a big number, it's better to do a calculator back there. Sounds
Do you
good?
mind showing? I'm sorry.
Go on, Wilson.
Can you repeat the steps on how to do it? The factorial on the calculator again?
So enter a number, and then you select math, and you go to PRB, and so you select option 4, I think, the exclamation mark.
Got it. Thank you.
No worry, Wilson. Okay. So you know, when you have a small number, it's easy to do with by hand, but you have a big number, it's better to use the calculators. Okay. All right. What do I do next? Next. Okay. So we have a bit left of chapter 5. Right about time for lunchtime. Right. So let's go ahead and take a 30-minute lunch break here. Then we come back. We look at the last two portion of chapter 5. Okay. All right, you can pause your recording now so that you don't.
27.
27. All right, because when you start a race, any of these 27 contestants will have the same chance of winning. So we do have 27 options. How about the second positions?
26.
26, all right. And then the third positions will be
25.
25. So that's what it is. So the total outcome, this can happen, will be 27 times 26 times 25. So we're looking at 17,550 different ways. Make sense? So that's what we mean by permutation. We don't finish the list of arrangement, but we only focus on what's important. So we want the first, the second, and the third. And this is an example of permutation. So if we look at permutation closely, we will see it's as follows. So permutation will have two conditions. Number one, repetitions of objects is not allowed, right? So when you do the counting without repetition, it's emphasized for permutation in this case. So repetition is not allowed, and the order is important, all right? So the order is important, meaning that AB position is very much different from BA positions. Okay, so if the dog A wins the first prize and dog B wins the second prize, if you flip them around, it's not going to make sense, right? Because dog B already won the second prize. So AB gonna stick with AB, right? Because the orders matter. If the first dog already win the first place, there's no way the second dog win the first place. So we cannot switch them around, right? So AB is different from BA. And that's what makes permutation distinct from other combinations. Okay, we're gonna see that later on. So those are the two conditions. Repetition is not allowed and order is important. So here's the formula for finding permutation. So NPR, right? So NPR will equal to n factorial divided by n minus r factorial. Okay, so n factorial divided by n minus r factorial. So you have how many outcomes, then you divide the one that you don't want to be in the list. So that's why we have n minus r. So if we apply permutation for example 7, right? If we apply n will be 27 and r will be 3, right? Because I want 3 position, first, second, and third, right? We want 3 places. So if I apply this method, so 27 p3 will equal to 27 factorial divided by 27 minus 3 inside the parenthesis factorial. So we express everything out. We're gonna have 27 times 26 times 25 times 24 times times 3 times 2 times 1 divided by 24 times 23 times 22 3 2 and 1. Now we can definitely do in some cancellation, and you can see how the logic works. So you do all the cancellation, and we get 27 times 26 times 25. This one's agree with what we have at the beginning. Yes? Okay, so when we do it with logic, right? We said, okay, how many chance I have for the first place? How many chance I have for the second place? How many chance I have for the third place? Versus with the formula, they agree with each other. Make sense? Just like conditional probability. Take a look at the formula, see how it works. Take up the logic to explain why it works. You guys got that? Yeah? Okay. So order is important. We have permutations, right? So if you want to use a calculator, then you just apply the rule here, right? So now we're gonna start with the outcome first. So I have 5, right? And I want to do math and then probabilities, and then I select NPR and whatever I want to do, I can just get that answer. So if I want to use a calculator for this kind of example, all right, so go back to the main screen one more time. So I have 27 contestants, and I want to select 3 to win first, second, and third. There we go, 17,550. So that's will be how many arrangement I can have for the first place, second place, and third place. Okay, are we good to go? All right. All right, next example. In how many ways can horses in a 20-horse race finish first and second? All right. So we look at the P will be 20 and R will be 2. So the number of way is equal to 20 P2, right? Because I know it's permutation because order is important, have to go first and then second. So I get 20 factorial divided by 20 minus 2 factorial. So technically we get 20 times 19, and that's just gonna be 380 ways. So we have to select 2 horses that finish first and second. So the probabilities of winning equal to 1 out of 380. There you go.
So if I had a more specific question, could I use this formula? Like instead of saying how many horses can finish first and second, what if it said how many ways can horses finish third and fourth?
So that will be because we're looking at first place and second place. And so in order for some horse to finish third and fourth, you're gonna get some horse finish first and second.
Mm-hmm.
All right, so you're gonna look at that possibility first. Then you have to look at, okay, I need to choose 4 horses in order 1, 2, 3, 4. You're gonna look at that total outcome, and now you look at how many way can I finish first and second, and then you look at separately how many way you can finish third and fourth, and then you do some more additional calculation on that. So here we just focus in consecutive arrangement here, 1, 2, 3. So we're not go too much deeper into that event. So here we just, so in 120, we just look at something very, systematic because this is introductory to probabilities. So for your question, that will go to the master level of probabilities.
Okay.
Okay, sounds good. All right, so the next topic is combinations, okay? So what is combination? How is that different from permutation? Now, combination also follow 2 conditions. Number 1, repetition is not allowed. So this is what is shared with permutation, right? For permutation, repetition is not allowed also. However, for combinations, the orders is not important. All right, for combination, the order is not important, meaning that AB is the same as BA. Okay, so AB is the same as BA, meaning that I don't really care who's win, but I just want to see, which one will take the first 2 places, right? Could be horse A take the first place, and then horse B take the second place, or it could be horse B take the first place, or the horse A take the second place. So I don't care which one will be the winner, but as long as I got the 2 leading horses, I'm the winner. And that's what it means by combinations, okay? So for combination, the formula will be a little bit different. So we have n factorial divided by r factorial times with n minus r factorial. So we not just divide out what we don't want, but we want to divide out how many times we are repeated that procedure. So that's why we have divided by r factorial right there, okay? So that's the major difference between permutation and combination. Okay, so that's the concept, right? So AB and then BA are different. Just like when you go order a pizza, right? So someone is very specific, like, okay, I want pepperoni first, and then I want pineapple after. Versus, yeah, just get me 2. You either get pepperoni and pineapple, or pineapple and pepperoni. Doesn't make any difference. I eat them both, right? So that's the difference between combinations and permutations. Combination, very strict order. Permutation doesn't matter, right? You can choose among the 3, right? So for example, we have an idea, right? So in our class, I'm gonna select 5 members. The first member selected will be the president. The second member selected will be the VP. The third member will be the treasury, and so on, right? So if you are first pick, then you will become a president, right? Or I said, okay, I'm gonna select 4 people. The first person who selected will get a $20 bill. The second person selected will get a $10 bill. So if you got first pick, you for sure you get $20, right? However, if I said I want to select 4 people, and when the 4 are selected, you can divide the money among yourself. So if you have first pick, doesn't mean that you're gonna get $20. You can get a $5, depend on how you guys divide among the group. Does that make sense? So very big difference between orders matter versus orders does not matter. Okay. Okay. So here we go. Right. Suppose that I want to choose 2 classes from English, math, history, philosophy, and art. So I have 5 classes to choose from. All right, so I have n is equal to 5, and then r is equal to 2. You can see here that I just want to choose 2 classes, right? So no order right here, right? So no order apply. So I can choose whatever the class I like. I got 2 classes. So in this case, we're just gonna do NCR. In this case, we have 5C2. So we get 5 factorial divided by 3 factorial and then 2 factorial. Okay. All right. So I should do that. All right. 2 factorial and then 5 minus 2 factorial. So that's give us 5 factorial over 2 factorial and then 3 factorial. So remember, 2 factorial times 3 factorial does not equal to 6 factorial. Okay. A lot of students say, oh, we can just multiply 2 and 3, but the answer is no. All right. So here's the reason why. So we get 5 times 2 times 3. Why am I doing that? All right. 5 times 4 times 3 times 2 times 1. Divide by 2 times 1 times 3 times 2 times 1. So you look at the denominator, the answer is only 12. But then when you look at 6 factorial, the answer is 720, right? So they are definitely not the same, okay? So 2 factorial times 3 factorial equal to 12, but 6 factorial equals 720. So they're not equal, right? Keep that in mind. And then you just simplify whatever you can. So you have that cross out. So you get 20 divided by 2, which is 10. So we have 10 options to technical classes from English, math, history, philosophy, and art. So you want to use the combinations option on the calculators. You can definitely do that too. For example, I want to do select 27 and hit math and go to probabilities, and then I go down to NCR and I just input 3, and there we go. So we have 2,925. So you can see here with repetition, the order, when the order is not matters, you are reducing the option so little compared to 27P3, right? So you have 17,550 for 27P3, but then when you look at 27C3, you only get around 2,925 orders, right? Outcome. So big difference. I'm gonna be very careful with that. So one wrong move can ruin the whole thing, right? And you might wonder, how do I know the best hints to recognize their differences? Well, you look at the card permutation, they give you a very specific detail, right? They want finish the first and second, very specific requirement. Up here, you want to have first, second, and third, very specific detail. When you look at combination, on the other hand, you can see here, I just said I want to choose 2 classes. There's no any specific order, right? Do you guys see that difference? There you go. Okay, and that's help us a lot in using the formulas. Example 5. From 9 names on the ballot, a committee of 5 will be elected to attend a political national convention. How many different committees are possible? So question, permutations or combination?
Combination.
Combination, because there's no order, yes? There you go, all right? So just need to select 5. Without any order. So combination. Therefore, 9C5, so we get 9 factorial over 5 factorial, times with 9 minus 4 factorial. So, so you can use a calculator, but I want to show, I want you to show your work. So this is what you need to do when you show your work. So this is how I want you to show work. Okay, so you can use a calculator, but I want you to write that down on your exam so that you can recognize, okay, which one is the total population, which one do I want to select, right? So just write that down and you can use your calculator. I'm totally okay, but then you need to know which one go first, which one go after. Does that make sense? Okay, so we get 126. Example 13. Winning jackpot in a California Powerball requires that you select the correct 5 number between 1 and 59. And in a separate drawing, you must also select the correct single number between 1 and 35. How many selections are possible? Question, permutations or combinations?
Combination.
Combination. Okay, so read it carefully. So you are familiar with the Powerball ticket, meaning that you're gonna select 1, 2, 3, 4, 5, and then the last one they call that the Powerball, right? So that's the separate ones. Okay, so let's look at them one at a time, right? All right, so I have here is you must select between 1 to 59, so that 59 number, so n equal to 59. All right, and r is equal to 5. So the first option I have will be 59C5, right? So a combination. All right, so that's for the first 5 number, and then for the last power number, we need to select one single between 1 and 35. So in this case, n equal to 35. So I have 35C1, right, for the Powerball. And this one here just 5 numbers. So multiply or add, which ones?
Multiply.
Multiply because it says
There you go. Okay. All right. So, and in the separate drawing, you must also select a correct single numbers. So it have to be multiplied. Right. So there we go. multiplication. So 59 over 5 factorial, and then 59 minus 5 factorial, multiply with 35 factorial, divide by 1 factorial, and 35 minus 1 factorial. Okay. 5006386 multiply 35. All right, we get 175223510. 175 million tickets can be sold. And each ticket, I believe they sell for $2, so they will make in around $350 million. Very nice, right? So each drawing, I think they start with 40 millions, and then they depend on whether we have winner or not. They keep increasing the price, right? So you can see here, I believe last year Powerball went all the way until $1 billion, right? You know, if you can imagine that it was in an expansion of 3 months, and they do their drawing every twice a week. So you know, each drawing they make around 350 times it by 2, right? So time six they work for 3 months, so that's 12 weeks. Right, time that by 12. So they do make more than $1 billion, even when the price is $1 billion, right? That's how it
So
goes.
if I were to buy 175 million tickets, I'm guaranteed to win.
Exactly.
Hmm.
And that's the reason why they have to do combination to attract more people to play. Yes. If they do permutation, yes, you still have a chance to win. If you number like exactly 1, 2, 3, 4, 5, 6, then you will have a chance of winning. But then that's reduce the amount of chances people are gonna win. Therefore, they have to be smart about it. They gotta do combination and not permutations. Does that logic make sense to you guys? The reason.
Not really.
Grayson, with permutation, the orders matter. Yes.
Yes.
So if your ticket is 1, 2, 3, 4, 5, and 6, and the winning ticket is 2, 1, 3,
Yes.
4, 5, 6, well, you can see number 1 and 2 in your ticket, and the number 1 and 2 in the winner ticket are switching. So you are not the winner because
Right.
it have to be in the order of 2, 1, 3, 4, 5, 6.
Yeah. See, the problem I'm having is that I don't know if I feel that like increasing the chances for the people is actually going to increase ticket sales, because already this chance is basically zero and people are buying in droves anyway. And most people don't understand probability. So it's kind of like, does your chances actually affect your ability to buy, or is it more just a pipe dream that you'll win?
No, of
Which
course,
will still be
because
there.
when they explain this, when they put out the statement, right? If you have a 5 matching number together with a Powerball, you win. Versus your matching number has to be in the order of our number, then you win. So that's give the people, okay, there's no way I'm gonna win, because they can flip around and say, well, your number and my number are not matching for one place, then we are not a winner. Versus there's my five matching numbers and the Powerball, I'm the winner. So that's how they play with the people.
Okay.
Uh-huh.
And it actually works.
It actually works. That's right. Uh-huh.
Okay.
Like when they crossed this out, right, Grayson, and they said your number have to be in the exact order of the winning tickets, no one gonna play Grayson.
Okay.
But then they outsmart people a little bit. As long as you got 5 matching numbers and a Powerball, you a winner. Easy, right? There we go. That's the idea. So will we still play? That's is why not, right? We still have 1 out of 175 million chance of winning, right? I know it's uncertainty, but it's not impossible. So that's the reason why people keep buying the lottery for that. But what really bothering me is that, all the big jackpot is not in California. It's always out somewhere in last time it was in South Carolina, right, and also in Michigan. So I haven't seen any big winning number in California yet.
Do they have a way of sending those tickets to different states? Like they use another formula to send different tickets to different states, or
Really?
just random?
Oh yeah, it's just random, Victor. One day in the machine, they just randomly do it. But again, a lot of people have a theory behind their logic, right? So we need to go deeper into that to understand how they run their system. But to generating the number of possibility tickets, this is how they do it, combination, Victor.
Sounds good.
Yeah, so there's a lot of rumor behind. There was yeah, we can send a winning ticket somewhere out there that's less popular, very less little people live, so that people in the city can buy more and more, we generate more benefits. But then the winning ticket is actually out there, right? So that's still myth that people make it up. Yeah. Oh, Matthew said you thought they have to be in order. That's why you still bought one. Now you can buy more, right, Matthew? Because you don't have to be in order, Matthew.
Yeah, my chance just went up. I'm definitely winning now.
Exactly. Your chances went up. So sorry, Matthew. Now you're gonna spend $20 a week now. Come on. Because of Mr. Bo. Yeah, so very funny story. My friend uncle, right? My friend uncle. So he have one number that he been building for 20 years. But the thing is, he always asked his wife to buy the same number for 20 years. And then there's one day he was like, come out loud and said, we are a winner because finally my number appeared. His wife forgot to buy it yesterday. There was one time that his wife forgot to buy the ticket, the number came out. And he's like, my 20 years of following. That's just crazy. Yeah.
That sucks.
I know. Yeah. Can you believe that? Follow the number for 20 years? Yep.
I cry.
Yeah, he cry a lot. Yeah.
No point of even playing anymore at that point. You missed
Exactly.
your one chance.
Exactly. Yeah, he followed that number. Yeah, I would go into depression, right? You've been following that number for 20 years, and there's only one time that you don't buy a ticket, the number came out. Yeah, but instead of spending like $100 to buy random pick ticket, you can just buy one ticket for every week. You still have a same amount of chance of winning. Yeah, right, Edward, right? That's right. Yeah, the reason winner did for the same for 30 years, but you're gonna keep buying continuously. Yeah. Okay, so all right, so that's one application that we would see. All right. So next up, we look at permutations with non-distinct item. Okay. So if the number permutation of n objects, which n1 have are one of kind and n2 are one of a second kind, and so on, then the total possible outcome will equal to n factorial divided by n1 factorial time n2 factorial, time n3 factorial. And this is something that you will see in, arranging something, or, a coin collection, right? You have 5 quarters, you have 10 dimes, and then 20 pennies. How many ways you can arrange them, right? You do see that there's a repetition in a quarter, there's a repetition in dimes, and then the repetition in the penny. So we need to take those away, right? So that's one application we can see here. And here is another application, right? How many different ways to rearrange the word statistics? Okay, so we just focus on the letters that repeat the most, and those are the one that we need to take away. So let's count how many letter do we have. So 1, 2, 4, 6, 8, 10. So 10 letter. So n is equal to 10. All right, so let's see how many times the s repeated. So s repeats 3 times. So n1 equal to 3, right? All right, so next most repeated letter. So T is 1, 2, 3. So T repeats 3 times. So N2 is equal to 3. And then next one is I repeats 2 times. So I repeats 2 times. So N3 is equal to 2. So we just worry for the letter that repeat the most, right? Because the one is just 1 factorial is just 1, so we don't focus on that. So we want to find out how many distinct arrangement for the word statistics. So we don't want the number to repeat itself too much, so we just take those away. All right. So the total outcome will be 10 factorial divided by 3 factorial, 3 factorial, and then 2 factorial, just like that. So that's something you can do in your calculators, right? When you want to use a calculator, you can have 10 factorial divided by parentheses 3 factorial times with 3 factorial, and then time with 2 factorial. Okay. There we go, right? That's the setup. That's the answer. So we get 50,400 different ways. Okay, so that's how you use the calculators. Yeah, 50440. Okay, so what we've been doing so far in 5.5, we just look at the total outcome possible that we can play around. So now let's go into the second half part of this, which is how do we find probabilities involve permutations and combinations. Okay, so same mentality will apply. Permutation involve orders, combination do not involve orders, all right? All right, so suppose I have a lottery ticket here, an urn contain ball number from 1 to 52. From this urn, you can see 6 ball without replacements, and then you put in $1 to choose a set of 6 numbers. What is the probability of winning? All right, so same concept. All right, I was mentioned before. total outcome will be 52C6, right? Combinations always. All right, so we get 2, 0, 3, 5, 8, 5, 2, 0. So we look at the probability of winning. You have one correct ticket out of that too many. All right, get pawn 0, 0, 0, 0, 0, 0, 0, 4, or 5, right? So let's back that. So again, it's uncertainty. Not impossible. Okay, remember very first sections of chapter 5, we talk about uncertainty versus impossible, right? So remember, impossible when the probability will be 0. I mean, unusual events is that have a very low probabilities, right? So we have that unusual probabilities right there. All right, number 16, a shipment of 120 fastener that contain 4 defective were sent to a manufacturing plant. The plant's quality control manager randomly selects and inspects 5 fastener. What is the probability that exactly one of the inspected fastener is defective? Okay. So for this kind of example, you do want to slow down and then do, one sentence at a time, right? So do a bit, read it through a few times, right? And this is why chapter 5 is tough for a lot of students, right? Okay, so I'm gonna read it through, right? A shipment of 120 fastener, so we know that would be N's right there, right? So N would be 120, okay? That's the total. So there are 4 defective fastener, right? So out of that 120, that would be 4 defective fastener. So you can imagine here I have a 120 item, right? 120 item. In this 120 item, I will have 4 defective. So if I have 4 defective in that 120 item, how many are non-defective?
116.
116, right? Okay, so that's what we know. Remember, 100 good iPhones and 500 bad. 100 bad iPhone and 500 good iPhone. Yes, that's the example. All right. So in 120, I know for sure there would be 4 defective, and then 116 that are non-defective. Now, when it's got to the factory, manager selects and inspects 5 fastener. Okay, so now out of 120, we're gonna select 5 to inspect. What is the probability of one of the 5 is defective. That's what they ask. You see how we break it down, the logic here? Yes, one at a time. 120, we know that will be 4 defective and the rest will be non-defective. So now go to the factory, run the manager, select 5 randomly. What is the chance that one of the 5 is defective? So when we think about this problem, say, oh, that should be simple. It's just going to be 1 divided by 5, but the answer is not right, right? Because there could be that when we pick those 5, there will be 4 defective will be picked, right? So we don't know it's going to be 1 out of 5 or not, right? Because we don't have 1 to 5 to select. We have 1 to 120 to select, right? So that's the big difference, right? So how is that different from what we learned before? So let me bring it back to you guys right now. So what we've seen in the previous example, right, in chapter 1, we are selecting 1 card. We have 1 dice, right? We have one coin is toasted, right? So we only select 1 card. And what is my chance of getting a deck of 52 cards? So my probabilities will be 4 out of 52, right? Because I only select 1. Does that make sense? Okay. So now if we go back to chapter 5 example, okay. If I go back to this problem that we are currently dealing with, okay, I'm going to make an if statement. If I select 1 object, right? If I select 1 fastener, what is the probability that it's defective? This is very simple.
1 out of 120.
Not 1 out of 120, a bit more than that.
4 out of 120.
There you go, 4 out of 120. Okay, does that make sense here, guys? We only select 1. We only put our hand in here and select 1 chance. Then we get 4 chances it's gonna be defective out of 120. But here we don't select 1, but now we are selecting 5, right? We are selecting 5. So this logic is not gonna work. Does that make sense? So we cannot rely on that logic, right? So if we select 1, then that's work, but now we're no longer selecting 1. We want to select 5 and see what the logic is. Okay, so out of 120, we select 5. Therefore, we get 20 C5. You agree? Combination, right? We just randomly pick 5 out of 120, so we get 120 C5. Okay, so that will be the outcome. So therefore, it will be in the denominator. Okay, so here is how we're gonna put this problem together. The probability that exactly 1 defective in 5 chosen is equal to 4C1 times with 116C4 divided by 120C5. Okay, so if you are convinced, thumbs up. If not, please ask.
Sorry, could you go over this last part one more time? Like, I get the concept of it, but I think I just need to like hear it again.
Okay. All right. I want to see how many people got convinced by that statement. With the formula, I put it down.
I'm a little confused by the top line as well.
I know, right? Yeah. It's okay, Matthew. All right. So that's why I want to throw it out there and see whether I say, oh, that makes sense. It doesn't make sense. Okay. I just want to see how many thumbs up do I see from that expression. All right. Any thumbs up? Let's see. No, I don't see any. Okay. Okay. I see one. All right. Who is that? Jackson saying, okay, Jackson got the idea. All right. So here's the logic behind that. How many defectives do we want? One.
Exactly.
Right? We want one defective. How many defectives we knew in advance? 4. So I want to see one will we pick in from this group, yes? So that's why we do 4 choose 1, yes? Now, how many do we choose to inspect? 5, yes? So if we choose 1 from the defective group, how many left do we need to choose? We have 4 left to choose, yes? And where are those 4 have to come from?
The rest of them, the pile of good and bad.
Them. And the rest of them will have 116. Does that make sense? And logic behind that. So we have to choose 1 from the defective group and 4 more from the non-defective group. Yes? There we go. That's the logic. Okay? So remember, total equal to 5. But 1 must come from the defective group. Therefore, 4 needs to come from non-defective. Now, does that logic make sense here, guys? Feel better? How about Julia?
Yes, I get it.
Okay. Wilson? Yeah, makes sense, right? So that's what I mean by we need to have a bit of logic when we do chapter 5. So we said, I want 5, but then what more specific requirement that they ask? They ask, out of those 5, how many that are exactly, so they want exactly 1 defective. So I have 4 defective. I pick 1 out of that group, so I have 4 C1. But I still need 5, so I have to pick 4 more out of the remaining, which is 116. And there you go. After you got that, you just put in the calculators and see what they give us. So we get 4 times this. What is 116 C4? So 7160245 and divide by 120 C5. So 190578024. All right, so we get 0.1503. Around 15% of that's gonna happen. Okay, what happened if I said I want exactly 2 defective? What will it be?
Would we change it on the numerator 4C2 times 116C2? Or Yeah.
Because the total has to be 5.
C3.
Right, Grayson? Yes?
Yeah, 4C2, 116C3.
That's right. And the denominator, we don't change it. That's
right.
Okay, so go ahead and test yourself out with example 17, please.
I have a question about example 16.
Yes.
You said that's 15%. What's that bottom number you wrote?
190578024.
And the top numbers, is it 4 times or 4.7?
4 times.
Okay, that makes a lot more sense.
Yes.
Thank you.
Because 4C1 is 4, and then 116C4 is the other one, yes. All right, so do number 17. If you can get that done, you got this concept. So remember, we all apply this when we choose more than one, yes? If we choose only one, then we don't have to go through this. We just go with what we learned before.
Professor, in number 16, the number 19057, where did you get that from?
When you do 120C5,
Okay, gotcha.
yes.
Sorry, this is probably a really dumb question, but when it says picture cards, does it mean like the ones like the royal?
The Jack, Queen, King.
Yeah. Oh, okay. Okay. Thank you.
Yeah, yeah.
Not a picture card, right?
Cards are the Jack, Queen, and King, yes.
Okay.
So I might have done it wrong, but is it 12C5 times 40C0 divided by 52C5?
You said 12C5.
Yeah.
40C0 divided by 52C5. All right. Anyone else agree with Grayson? Going once, going twice. Bingo. That's the correct answer, Grayson.
Okay. Thank you.
Why is a C0 on the 40? That was the only thing I got different.
Because the total is 5, but then you said all 5 cards must be picture cards, so there's no chance left for the number cards. That's why he chose 40C0.
Got it, yeah.
Would it make sense to just leave the 40C0 out when you're doing like when you're solving the problem, like just to make things faster?
Okay, so the reason Grayson put it down is that so that we don't mistakenly only do one at a time, right? What happened if they said here that 4 picture cards? Then when we throw out this option here, then people would just say 12C4 divided by 52C5. That's what you're gonna do, because I said, yeah, when the previous example, well, we only did 12C5. So now if you choose 4 picture, then it's gonna be 12C4. But now it's not, because you have to do 12C4 times with 40C1, right? So that's the reason why Grayson said, I'm just gonna stick with that, follow the rule, right? And even though it's a little bit slower to do, but it will guarantee the right answer every single time. If I change that to, I don't want 5 cards anymore, but I want to get 5 picture cards, then that's what you need to do.
Okay, thank you. So like on the exams, you want us to like write out all of this as well for like
That's right, because it's not going to be guaranteed that I will show you 5 picture cards, right?
Okay. Thank you.
So does that logic make sense? There we go. Okay. So remember. Okay. Let's go back. Let's go back to the first section of chapter 5. How we did that example, right? All right, so the one that I show you for, where was that? Okay, so if a card was drawn from a deck of 52 cards, what is the probability that the card is a 10? Can we do a combination? The answer is absolutely yes, right? So here we go. So we have 52 C1, that's a total, you agree? And then a card is a 10, so there are 4 10s, right? So there you go, probability a 10 will be 4C1 times with 40C0 divided by 52C1. And 4C1 will be 4, and 40C0 will be 1, and 52C1 will be 52. So that's why we got 4 out of 52. That's how we explain it. But then, you know, you only pick one card. Would it be faster to do 4 out of 52? Then we have to go through combination. Absolutely, right? However, combinations will decide for if we choose more than one card, because we have to look at the possibilities. So I can choose a 10 first, I can choose a 10 after. We have to look into all that possibility. And that's the reason why in the last example, we don't choose one single card, but we decide to choose 5 cards. And therefore, we apply combination on that. Make sense? Yes, Aaron.
On the example that you just showed, if one card is drawn from 52, what's the probability of it being 10? Can you go back to that one for a second? Because I have a question about that one.
Okay, let's see. Yeah, go on, Aaron.
So yeah, how come it's 4C1 times 40C0?
Not 40, 48. Yeah.
Oh, okay, that makes sense. Okay, thank you.
I got mixed up with the picture cards. Yes, Matthew.
I got a question about example 16 again.
Okay, sir.
So once you pick the correct fastener, so let's say you pick the correct fastener first, wouldn't that change your overall percent of the rest of them? Because the rest of them you're grabbing at, there's less bad fasteners in there.
Yeah, but we don't know whether
what I mean?
the first time you pick gonna be the defective one.
Oh, got it. So this is the probability before you pick any of them.
Exactly.
Once you pick one, it's going to obviously change.
Exactly, right? So this is
that
all
makes sense.
behind the desk.
Okay, I get you.
This is all behind the desk, because if you go out there, you pick, oh, the fastener, my job is done, right? That's too easy. But then, you know, when you look at behind the desk, say, okay, if I would have to go out there and inspect, what is the chance of getting a defective one? My chance will be 15%, meaning that if I pick 100 times, 15 times, I will pick the defective one, right? So that's the idea.
Mm-hmm.
Yeah, all of this, Matthew, are all theoretical probability, not actual probabilities.
Okay, yeah, I'm probably going to mess it up for a while.
Yeah, don't worry. Okay, so you know, sometimes think simple, right? So like, oh, what's my sense of that? Okay, all right, sounds good. Okay, so that's yeah, go on, Austin. Austin, you raise your hand. Go on.
Sorry, my mic was muted twice.
Worry.
So just so I got this right. So if the problem said, or if the question said, find the probability that 4 of the 5 cards are picture cards, that would be 12C4 times 40C1. Okay, cool.
Mm-hmm. Makes sense now, Austin?
Yeah, that makes sense.
Okay, all right. So that should be the end of chapter 5. Okay, 5.4 and 5.5, those are big, so we spend that's today. So tomorrow, I'm looking at chapter 6, and then Thursday will be full on review, right? So hopefully by Thursday, you will do a lot of problem already, and then you can ask any question on that review package to get us ready for Monday exams. You know, when you come back on Monday, if you still have further questions before the exam, let me know, I can answer that. And I think Edward already sent out the survey for the tutoring section, and I believe he also have some more. Edward, do you have any more additional information on that survey?
Yeah, so it seems like everyone is counting in for 3 o'clock or 3:05 today.
Okay.
Whoever came yesterday opted in for that time. It was a very small percentage that people wanted a later time, so I'm going to go with the larger percentage. But for
is there any chance you can run an additional section on Friday, Edward?
Yeah, I'll definitely I can definitely try to fit that in. I don't see why that's a problem. I'll let y'all know. Oh wait, I can actually see the time for Fridays. Thursday, Friday, Saturday. Oh, I see. So some people really like the tutoring on the weekend for Thursday, Friday, Saturday, for 2 hours a day. That was 100%. But for Friday, it seems like 60% of the people who came yesterday want to start on Friday at 3:30.
Yeah, if you want to run on Saturday, Sunday, that's totally up to you. But I just want to see if you can run one more additional tutoring hours before the exam, right? Especially before the exam, they're probably going to have more questions to ask. So
Yeah.
I don't know if 1 hour will be good enough for students to express, a lot of students to ask questions.
Yeah, I think I can go for an extra hour on Friday at 3:30 to 5:30. So I'll fit that into the schedule, and I'll announce that and put that under the announcements as well.
Thank you, Edward.
Yeah, of course.
All right. So please looking forward for that email that Edward going to send out on Friday. Okay, guys?
Yeah, so today at 3:05, and then I'll send that link on the announcement soon.
Thank you. Okay, so tomorrow we cover chapter 6, and that will be it on the exam next Monday. Okay, so we're not gonna go stressed out to chapter 7 to save that for the second exam. All right, I'm gonna take attendance real quick. If you have a question for me, stay around. If not, after I call your name, you can log off. All right. All right.